Hello, and welcome to designing a flyback DC to DC converter. In this video, we will discuss the flyback transformer once more, as it is the most important component of the flyback converter and is a specific transformer. Then we will finalize the design. My name is Brigitte Hauke. I am Boost and Buck Boost Controller Application Manager in Texas Instruments. This video is the fifth one of a video series which concentrates on the flyback converter design and gives some guidance for practical issues. Let's have a look on the flyback transformer. As discussed in the operating principle in video 2 of the series, the current in the transformer is either flowing in the primary winding or in the secondary winding. So a flyback transformer is not a real transformer and has to be designed differently. The flyback transformer has several, at least two windings on one magnetic core, but it is at the end a coupled inductor. It is called coupled inductor because it stores energy like an inductor, and through the single magnetic core, the energy is coupled from the primary to the secondary side. This is different to a real transformer. A real transformer transfers the energy directly and instantaneously from primary to secondary side and does not store the energy. So the design of a flyback transformer is different from the design of a real transformer. So using transformers that are said to be useful for flyback and other topologies are in general compromising the performance. We recommend designing a fitting flyback transformer for the specific power supply, as this is the most important component. It directly impacts the performance of the converter. Here is a list of basic requirements of the transformer. Saturation has to be avoided at full load. If it saturates, no energy is stored and it will most probably damage the MOSFET. Normally, the flyback transformer is designed as a compromise between the inductance and the frequency of the right half plane 0. It shall be physically as small as possible, for example, for having lowest cost and best core utilization. The power loss in the transformer shall be within a not too big range, so around or below 3% of the full output power. The losses shall as well have a good balance between winding or copper losses and the core losses. For magnetics design, I recommend reviewing the Magnetics Design Handbook from Lloyd Dixon. See the first link in the bottom left. More details on designing a flyback transformer can be found in the application note Flyback Transformer Design Considerations for Efficiency and EMI. The link is here, the second one on the bottom left. Let's have a look on how the transformer was designed for this specific flyback converter. From the parameters calculated in video 3 of the series, an EP13 core was selected. The selection process is often as well an iterative process, as the physical design and the necessary windings might not fit into the first selected core, or the core is much too big. The EP13 3F3 core is a good choice for these specifications. The effective area of the core is 19.5 square millimeters, and the inductance factor is 1325 nanohenry per turn for an ungapped 3F3 core. You can find these parameters typically in the core datasheets. According to the datasheet, the necessary magnetic flux density, B, needs to be below 3150 Gauss or 0.315 Tesla. Here you can see the calculations of the maximum flux density for two different number of turns. You could as well calculate the minimum number of turns with the given maximum flux density of 315 millitesla. In this case, it would be 12.8, so at minimum 13 turns. but for getting full turns for the other windings, I used 14. With this information, a magnetic vendor like Würth can produce an appropriate flyback transformer. I recommend testing and optimizing the transformer, so keep in mind to spend this time for a good flyback converter. Let's have a look on the transformer that I received from Würth. Here you can see the first page of the datasheet as well as the link to the transformer from Würth. Let me show you a bit more details of this transformer. Here you can see the page that I copied into the presentation, and on the second page of the datasheet you can see that this transformer is designed for the application discussed in this video series. Now let's have a look at the final steps for designing a flyback converter. As you can see, this is the design of the LM5155 flyback evaluation module. You can get this evaluation module from Texas Instruments and, for example, create a more optimized transformer for this or your design. Now, after these 5 videos, you should have a basic understanding of all needed calculations for a flyback converter. Let's now jump to a topic that makes or breaks any converter: the layout. Be aware that our datasheets typically include layout guidelines. Take care to read them thoroughly. And if evaluation modules are available, try to get close to these layouts as they are typically tested and optimized. The first point that you have to keep in mind for every layout: current flows in loops. Do not forget the return path for all current loops. Make sure you design the return path as well. Check for the high current paths and place the components in a way to minimize these current loops, especially if the currents are AC currents, like through the switch or diode. Use as much copper as possible for high current paths. We often use 2-ounce copper on the outer layer to minimize parasitic effects. For the gate drive, it is best to route the return path directly below or above the path from the IC to the MOSFET. As long as the outer layers are used, the area of the current loop is reduced as much as possible. Make sure to separate analog and power grounds to minimize ground shift on the sensitive signals like feedback. Use one single point connection between analog and power ground to make sure you do not get circulating currents between them. Make sure to keep the MOSFET, the transformer, and the diode as cool as possible by using thermal vias. These vias shall be a lot in parallel and small enough that solder does not flow through them. In this video, we discussed about the so-called flyback transformer, which is in reality a coupled inductor, and about finalizing the design. The 6th and last video of the series gives some answers to frequently asked questions to flyback converters. You can find further information, for example, in the E2E forum or ask your question there. A lot of details can be found on the product page, for example, flyback evaluation modules, application notes, models, or design calculators. In addition, a lot of reference designs are available at the Texas Instruments webpage through this link. Thank you for listening.